In section 5.1, we're going to review net area under a curve. We talked about that at the beginning of the semester. We're also going to review Riemann sums that are used where we use rectangles to estimate the net area when geometry can't be used. And you can see up here, we're tying section 5.2 together in this same video because 5.2 is really nothing more than introducing I shouldn't say introducing, even reviewing a little bit of notation, but then taking the idea of limits, putting it together with Riemann sums, and actually being able to calculate the exact net area when we're working with a curve. Okay, so in our first example here, we're looking at the function x cubed minus x, and I've drawn a rough sketch here. It's a pretty terrible sketch, but it's close enough to what we're dealing with here. So a quick review first is when we're talking about net area. First of all, we're typically going to be told over what interval to be looking at. So we're just going to look at everything that I just graphed there from -2 to 4. And just make sure that we have a visualization of exactly what we mean by net area. So the review here is that net area is nothing more than the area between the graph and the x-axis. If you're above the x-axis, the area is positive. If you're below the x-axis, the area is negative. And so here we're going to have to break it into some chunks because the area between the x-axis and the graph changes in the direction as we go across here. So all I mean by that is if I'm looking at -2 here, where my area starts, the area between the graph and the x-axis is this little almost triangle right here, right? It's not down below or up above here. It's just this little area right there. It's below the x-axis, so that area is going to end up being negative. As I move between -1 and 0, the area is this little hill above the x-axis that is positive since it's above the x-axis. The area between the graph and the x-axis between 0 and 1 is, again, kind of the valley. That area would be negative. And then finally, I don't think I quite drew it over far enough, so just pretend that I did. I'm stopping at x is equal to 4, and I'm looking at all this area here between the function and the x-axis. And of course, that's on the positive side, and so we're looking at a nice positive area. Okay, so that was just a reminder what net area is. We're not actually calculating net area in section 5.1 because we're not working with anything that had straight lines. Okay, so if you remember, again, when we were doing this at the beginning of the semester, the only time that we could actually calculate the net area exactly was when we had kind of straight lines where we can form our own rectangles or triangles or even trapezoids if you wanted to and use geometry. Okay, but of course, we work with curves for the most part in calculus, which is why we talked about Riemann sums. So a Riemann sum, just generically, is nothing more than using rectangles to estimate the net area. Okay, so we'll do one in a second. I don't want to draw the representation over here quite yet when we're just generically talking about it. But the idea is nothing more than you can fit rectangles at least around the curve, either under or slightly above or maybe exactly on the curve. But you're just using rectangles to estimate what is the area under there, because we can certainly just use base times height to get the area of a rectangle. The more rectangles you use, the more exact our estimate is. Okay, so that second part is what we're going to kind of dwell on at the end of section 5.1 into section 5.2. Right now, we just need to have a quick review of how this works. Okay, so generically here, let's say that we're working with a Riemann sum, and we'll be a little bit more specific down the road when we actually do a calculation. But if we're doing a Riemann sum, let's say over that same interval from -2 to 4. And let's keep this nice and small so that we don't have a whole lot of calculations here. But let's say we're using 3 subintervals, which is really nothing more than saying that we're using 3 rectangles. And our textbook likes the word subintervals so that you can see how this is broken down into rectangles. But all it's saying is take that area and split it into 3 rectangles in order to estimate it. And so at the beginning here, we don't even need to know whether we're talking about a left Riemann sum, a right Riemann sum, or even a midpoint Riemann sum that we'll talk about this time that we didn't really talk about previously. In no matter what type of Riemann sum you're dealing with, we can calculate the base using the information that's given to us just right here. Okay, we don't even have to use the graph. We'll come back to that in a second, but the base of every one of these rectangles is coming from the x-axis. So here, this is our interval on the x-axis. It's 6 units long. We're breaking it into 3 rectangles. 6 divided by 3 gives us that each excuse me, rectangle has to have a base of 2 units. And so putting this in formula form to follow the textbook, the length of the interval you get by just subtracting, and you're dividing it by the number of subintervals. And as we said a second ago, that's just going to give you a base of 2 units for each one of our rectangles. And kind of keep this in mind that our textbook does use some different notation from time to time, more specifically so that we could put it in some technical notation later on. But the base of each rectangle is the same thing as how much your x value is changing as I move across the rectangle. So that's why that notation is used here. Okay, and so just taking a look over here, if you had a visualization, all this is really doing is saying, well, we're going to use the x-axis as the base of our rectangles. This is 1, 2, 3, 4, 5, 6 units long. That means I need a rectangle spanning from -2 to 0, from 0 to 2, and from 2 to 4. That's all that was saying. Okay, and then before we start to break this down into left, right, and midpoint, let's just go ahead and write out what I just put on the board. I don't want to have to label it over there, but the endpoints of our subintervals, these are not necessarily left endpoints or right endpoints or anything like that. They're just all the endpoints. We have endpoints of intervals at each one of these markings that I put over here. So we have an endpoint at -2, 0, 2, and 4. And if you didn't have the visualization, all that is we start at -2, move 2 units to 0, move 2 units to 2, move 2 units to 4, until we're all the way through. Okay, so now just bear in mind, we can't just use all of these endpoints for my Riemann sum, because there'd be 1, 2, 3, 4 calculations, but we only have 3 rectangles. So it's important that we pick out the correct endpoints to use depending on whether we're working with a left, right, or midpoint Riemann sum. Okay, so we can point back at the picture if that helps, but it's listed right here. If we're looking at a left Riemann sum, we are looking at getting the heights of our rectangles from the left endpoints. So the left endpoints would be the 3 endpoints that are on the left side of this list. If you're looking at it visually, if I look at this interval, it's the -2 that's on the left. If I look from the 0 to 2, the 0 is on the left. If I look from 2 to 4, the 2 is on the left. So we're using the left endpoints here as our x values to evaluate to find the height of the rectangle, and we're not using the 4 at all. So the Riemann sum is nothing more than adding up all of the rectangles, or the areas of the rectangles. The base of every one of these rectangles is 2. So the base of the first rectangle working from left to right is 2. We have to multiply that times the function evaluated at that first left endpoint. Then base times the height of the next rectangle is getting from f of 0 plus the base times the height of, base times the height, we're getting the height by evaluating f at 2. Okay, so that's all our left Riemann sum is. It's basically making sure that we can keep track of the information, come up with our base, our endpoints, and then evaluate appropriately. So if you take a look at -2, if you plug that into our function, don't use the graph here because I'm a terrible drawer, but put it into the function. -2 cubed is -8, minus the -2 is going to give you a -6. Watch your signs there. F of 0, if you put 0 in for x up there, everything turns into a 0. And then if I look at 2 cubed is 8, minus 2 is +6. Whoops, I have an extra x or f in there. So that last function gave us 6. And now it's just arithmetic. The 2 times 0 disappears. This gives you -12. That gives you +12. -12 plus 12 also cancels out. And so your left Riemann sum here is a 0. Okay. And now just taking a look back here, I know that this seems kind of silly that there's no way the area is 0, but it's maybe a little bit closer than you might think at first glance. And kind of looking over here, because of symmetry, it really appears like these are the same size. One's positive, one is negative, so it makes sense that these kind of cancel out. And likewise over here, we have another positive negative, and so there is going to be more canceling here. But I think you can see visually, this area is much larger than this area down here. And so the actual net area should actually be positive. So the 0 that we got here is kind of the result of, excuse me, this being overestimated, this being underestimated to the point where they match up and they cancel out. Okay, but again, that's why we want to use more and more rectangles to get a better estimate here, but that's the left Riemann sum. And so if I'm going to be looking at the right Riemann sum next, the only thing that changes in terms of the calculation is which endpoints we're using. And we're still going to be taking base times height, so on and so forth. But if I'm looking at a right Riemann sum, we have to be looking at the right endpoints. And surprise, the right endpoints are going to be the 3 endpoints on the right. Okay, again, just visually, right endpoint at 0, right endpoint at 2, right endpoint at 4. Okay, but that's exactly the same thing as just taking the end of our list instead of the beginning, if you want to look at it that way. Okay, and everything else here is just calculation. We already figured out that f of 0 was 0 and that f of 2 was 6. We haven't done f of 4, not too hard. 4 cubed is 64 minus 4 is 60. And so here, 2 times 6 is 12, 2 times 60 is 120, add 12 and 120, and we're going to get 132. Okay. And so, this is kind of the opposite of what just happened with the left-hand endpoint. With the left Riemann sums, we ended up kind of overestimating this area and underestimating this to the point where they were kind of the same size. Now we're actually exaggerating. This area is being underestimated, this area is being overestimated, and so we get a huge sum. Okay, so that also is not exactly reasonable, but it somewhat makes sense because this area is actually much larger than this area over here. It's just not that much larger. So right now, our two estimates are really far apart, right? Our left Riemann sum was 0, our right Riemann sum was 132. Again, that's why down the road, we're gonna start using more than just 3 subintervals. Okay, so the last thing that we want to just take a quick look at, because this is actually not used terribly much because of the nature of limits going forward, but we also have a midpoint Riemann sum. If you're going to do a midpoint Riemann sum, we better find the midpoints of each one of these intervals. And this is nothing more than just looking what's the number that's halfway between -2 and 0. It would be -1. Halfway between 0 and 2 is going to be 1. Halfway between 2 and 4 is going to be 3. Yeah, that's all we mean by midpoints. I'm not going to write this out with every one, but if we were working with trickier numbers here to where we weren't getting nice whole numbers as your midpoints, your formula is nothing more than remembering that the midpoint is the average of the endpoints. So if you really needed to, you could say, well, the first midpoint would be the sum of the 2 endpoints, right? The average, you add the endpoints together and then divide by 2 since there's 2 numbers there. And of course, that's going to give you the -1 that we just came up with. And don't do that work if you don't need to. I'm just pointing it out that if you get unlucky with maybe some of the My Math Lab assignments, you might end up with endpoints here that are at, say, -1.5 and +1/4, so on and so forth. So we need to have at least a little bit of a way of coming up with that. So finally, though, if you know those are the midpoints, then the midpoint Riemann sum is nothing more than the same thing we've been doing, just use the midpoints. So base times the height. The height this time is going to be the function evaluated at -1, plus base times the height, plus base times the height. And now just, again, do the arithmetic. If I put in -1, -1 cubed is -1, minus the -1, it's going to give you a 0. Again, watch your signs there. I put in 1 cubed is 1, minus 1 is another 0. And then 3 cubed is 27, minus 3 is 24. Of course, the first 2 just disappear, and 2 times 24, hopefully you guys can see this, is 48. Okay. And so, excuse me, this, I'm not saying is a perfect answer, but as you might imagine, it kind of splits the difference between a left Riemann sum and a right Riemann sum. And if you were really constrained and didn't have the time to do the calculations we're about to do, the midpoint sum is typically going to be more accurate than the other two. And just to make sure that I show one of these, we've done tons of left and right Riemann sums previously, but never a really midpoint sum. If you're looking here with the midpoints, you would say, well, the function value at the midpoint is right there, so we don't really get a rectangle. Okay, but at the beginning it seems, well, that's stupid, that just kind of canceled out. But the positive area and the negative area, they're not quite the same, but they're pretty close to the same amount here. So that's why the 0 makes sense there. If I look at the midpoint of the next interval, it's also at 0, so I don't really get any rectangles. It's kind of coming straight across. And once again, it's not perfect, but these two areas are very close to the same amounts. And then finally, if we use the midpoint of the next interval, we're getting a rectangle that looks like this. So over here, it's overestimating on one side, right, because this is higher than the function. On the other side, it's underestimating because it's lower than the function. And it's not perfect, but oftentimes the amount that you're underestimating and the amount that you're overestimating kind of cancel each other out and gives you something pretty close. And so that 48 is, out of those three, it's probably by far the best estimate that we have. All right, so that was, kind of all the details, the rundown between the different types of the Riemann sums. And that's the main idea to remember from section 5.1. But in order to do section 5.2, we're going to have to get used to using other notation and using some ideas from algebra so that we can deal with Riemann sums that have 100 rectangles or 50 rectangles, or just n rectangles that we can take the limit of later on. Right, so next part is hopefully a bit of a review from algebra, where we have special notation that we use to indicate sums. Right? We don't want to have to write something like 1 plus 2 plus 3 plus 4 plus 5. We want to be able to do this a little bit more easily. So this is the Greek letter sigma. That's why it's called sigma notation. In the Greek alphabet, this is the same as the letter S. And so here we're just talking about S for sum. Right? So if we have, say, the sum from 1 to 5 of the variable here doesn't matter. We'll talk about that in a second here, but we have to have some sort of representation of what we're adding. What this is saying is take this expression, which happens to be k. We don't need to do anything special here, but just take this expression, evaluate it at 1, write it down, evaluate it at 2, write it down, all the way up to 5, and write it all out. So, this is something that we're going to have shortcuts to calculate as we go forward, but this literally means start with 1, add 2, add 3, add 4, and add 5, and that's it. Okay. So, if we were actually calculating this, we would add these together. 3 and 3 is 6, plus 4 is 10, plus 5 is 15. So if anybody cares, that's the actual answer. But this is what it means. It literally says to start at whatever number this is and end at whatever number the top is. So this is called the lower limit and the upper limit. And you are counting by ones every single time. That's always understood here. We're not counting by twos. We're not counting by 1/2. We're not trying to hit every little number that's between 1 and 5. We're just talking about integers increasing by 1. Okay, so that's all that's going on there. I guess I should go ahead and write this. If we're just working with something that's relatively straightforward, you don't have to write anything specific within your sigma notation. But as we go forward, we're typically going to go ahead and label the bottom or the lower limit to make sure it's clear that we're saying k is equal to 1 and then k is equal to 2, so on and so forth. That becomes important if you're summing different ideas, which we'll see in a second. But in this one, it was kind of unnecessary. So just keep this nice and small. If we said this time around that we're going from k is equal to 3, from 3 to 6, and we're summing maybe 2k plus 1. Now let's just leave it like that, 2k plus 1. Now it's the same thing. You're putting in k equals 3, then k equals 4, then k equals 5, so on and so forth. So if I put in 3, 2 times 3 is 6, plus 1 is 7. If I put in 4, 2 times 4 is 8, plus 1 is 9. If I put in 5, 5 times 2 plus 1 is 11. If I put in 6, 6 times 2 plus 1 is 13. And that's where I stop. Right? It didn't say to put anything larger than 6 in there. So now you just add this up. This is 16 plus 11 is 27 plus 13 is 40. Okay. So that's the basics of what sigma notation looks like. I guess one more example, because every once in a while, you're not actually going to be summing up numbers. You might be summing up expressions. And so let's get rid of this and just take a look at what that looks like. It's really not any different, same meaning, just a slightly different look. So let's say that we're looking at the sum from k equals 2 to 4 of k n squared. Okay. So this looks maybe a little bit scarier, but this is really not so bad at all. Okay. So if I plug in 2 for k, and this is where it becomes a little bit more important. If you have more than one variable up here, you have to know which one is the variable that's changing as we add these things up. So it's k that's changing. That n squared is not changing here. It's just going to keep staying put. So if I plug in the 2, you'll end up with 2n squared. If I plug in the 3, I'll end up with a 3n squared. If I plug in a 4, I'll end up with a 4n squared. And that's where we stop, right? It said to start with k equals 2, end when k is equal to 4. And so not a huge difference between what we just did. There was just an extra n squared there. Okay, but all it takes is one small change to the notation. Change that the k equals 2 to an n equals 2 here, and have that same expression. Now, of course, it's different. It's now k is staying put, and we're putting numbers in for n. So just to be clear here, we would replace n with 2, and then n with 3, and then n with 4. And I know that was probably unnecessary, but I wanted to make sure it was clear how those were getting plugged in, since there's 2 different variables. And then you're evaluating. 2 squared is 4, 3 squared is 9, 4 squared is 16, and then adding these guys up. So 13 plus 16 is 29. Okay. And so obviously it makes a huge difference with what variable you're working with as you sum. Okay, but the moral of the story is, if you're working with plugging numbers in for k, the other variable is going to be left over when you're finished, and vice versa. When you plug numbers in for n, it's the other variable k that's left over when you finish here. Okay, but those are the just the main ideas of what we're talking about when we're using that sigma notation for doing sums. Right, so there are a bunch of properties of sigma notation that we can use along the way, some of which are more important than others. I made a list here to make sure I didn't forget about any of them. But these are all found on page 344 and 345 of your textbook. So just as a heads up, there's a couple formulas that I'm not writing down in the notes here because they're somewhat rarely used, and you can certainly just look it up on your own, knowing that this is where it's at in the textbook. But the first piece that we have here is it does not matter how far you're counting, but typically in the problems that we do going forward, we're typically always going to start with 1, and it doesn't matter how high we count. All of these properties are going to work. If we take a constant and multiply it times some function being evaluated at k there, then notice the constant here is not changing as I put in different numbers for k. I'm going to have c times f of 1 plus c times f of 2 plus c times f of 3. That c is going to end up being a common factor that you can factor out. And this is no different than taking the constant times the whole sum. So all you're doing is kind of changing the order of what you're doing things in. But that's not something that's universally true. This has to be a constant. If there was another function in here that involved the k, you can't pull that out because that's changing with each term. But that's a constant in every single term. That makes it a common factor. So if you have a constant multiplication, you can pull that out. Okay? The next one, again, doesn't matter how far up we're counting, but let's say that we're summing up two different functions that both involve a k here. Okay, so this one I'm not going to try to talk through as much, but I think this is clear that since this means to add up and we're adding here as well, we're just going to have a whole bunch of adding that we can kind of rearrange. Instead of putting f and g and f and g and f and g, I can just rearrange it, right? F, 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 and then G, 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 G. That's the same thing as just breaking this down. Whoops, got ahead of myself. Is breaking this down into two different sums. I know that seems like it might not be beneficial, but because of the formulas that we get for evaluating some of these sums, it's always nice to be able to break something down like this. Okay, so I don't want to overdwell on this, but this is a constant multiplication property. It's very similar to the same constant multiplication property we had for derivatives and for antiderivatives, right? If we're taking the derivative, you don't have to take the derivative with the c in there. You can take the c out and then take the derivative. Same thing with the antiderivatives. If you're working with the derivative of two functions, that's the same thing as taking the derivative of each function. So I'm trying to make sure that we tie in the fact that these summation rules and limit rules and derivative rules that we've had, they're all very similar when we're working with constant multiplication or just addition or subtraction. Right, so those are generic rules that we're going to be able to use to break things down, but the actual calculation rules are what are going to allow us to do some interesting things as we go forward. So this time around, still going from k equals 1 to n, let's just say that we had a constant there. Nothing that depended on c whatsoever. If we added this up, we would say, well, if I plug in k equals 1, I get the constant. If I plug in k equals 2, I get the constant. If I plug in k equals whatever, I get the constant. So that's just the constant time added to itself. How many times is that happening? Well, counting from 1 to n, certainly going to be n times. So this is just n times whatever that constant is. Or if you prefer, c times n, but either way, that's all that happens. If you have a constant, you just multiply it by however many terms you end up with. Okay, so that's how you can sum up a constant. And I'm not going to exactly, I'm not even going to try to explain in a shorthand manner, how to get this formula. If anybody's curious, shoot me an email, and I don't mind trying to talk through it with you, because it's, again, just kind of rearranging. But it turns out here, excuse me, that if you're just summing up a bunch of just the variable itself with nothing else happening to it, that there's a formula that just depends on your endpoint here, right? The 1 is this every single time. The variable matches the k that's down here. That means that the k is changing. We're putting numbers in for k. The only thing that we're going to have left at the end is is an n, because that's the only thing that's kind of the actual difference between the different examples you would run into. So this ends up being n times n plus 1, all divided by 2. Okay. So just a very quick illustration of this is we saw not too long ago that if I go from k equals 1 to 5 of k, we said that was 1 plus 2 plus 3 plus 4 plus 5 in our introduction, and ended up saying that that was 15. Well, just make sure that it's clear here. If I take 5 and plug it into this formula, you would have n is equal to 5. 5 plus 1 is 6, divided by 2. 30 divided by 2 is 15. So that's just verifying that the formula works and kind of putting in the context of something that we've already done. Right, so the couple formulas that I'm not writing on here that are on the page 344 and 345 is there's actually a formula for what you get when you sum up k squareds. There's another formula for summing up k cubes. Those are some things that you can look up and find the formula on their own. It's just a little bit longer to write. I don't think it's beneficial to put it in the video. All right, so finally, let's just do one. This is kind of completely out of context with the Riemann sums and such, where we're putting all of these rules together. So let's say that we're looking at the sum from k equals 1 to 25 of the fraction 3k minus 1 over 4. And I guess those parentheses are probably unnecessary. But anyway, this is our practice. First time we've done anything where we're adding up like 25 different objects. That's a little bit much to write it all out. So all we're going to do is use the different properties that we just had on the board to kind of rewrite this and reorganize it so that we can use the formula and come up with this without having to write it all out. Okay, so the first thing to hopefully recognize is that we are just dividing this expression by one term in the denominator. So that expression itself can be rewritten so that it's a little bit easier to see what's about to happen. 3k divided by 4 is the same thing as 3/4 k. And -1 divided by 4 is -1/4. Okay, so the first thing we'll do is just separate the fraction out. Then after that, we said earlier that the sum of an expression here is the same thing as the sum of each individual term. So that was one of the general formulas. So again, we're keeping the exact same upper and lower limit, but this is the sum of 3/4 k plus the sum of, well, sorry, not plus, that was subtraction up there. So this should be a minus. And then I'm going to kind of cheat so that I don't run out of space here. But we also have the constant multiple rule. So be careful, don't use it too fast. This is 3/4 times k, but that's just on the k. It's not on the whole thing. So there's nothing we could do here except for break up our subtraction. But now because the 3/4 is a constant, we could throw the 3/4 out in front of our summation. Okay, so we use the sum rule and the constant multiple rule to get this broken down into 3/4 times the sum of k minus the sum of 1/4. And now it's just a matter of using our formula. The sum of k was the last formula we had previously that I've erased, but our formula for that was to take n times n plus 1 and divide it by 2. And so that 3/4 just came down, and this was the formula that we saw just a moment ago. Okay. And then we're subtracting. This time around, we don't have any sort of k. This is just a constant, so we're adding the 1/4 25 times. Well, that's the same thing as taking 25 times that 1/4. Okay. And then the rest of this is just use your calculator or whatnot. I'm not going to show all the arithmetic here along the way because I think everybody in the class would just type all this in your calculator. So depending on how you want to look at the answer, you either get 950 divided by 4 in fraction form, or if you actually divide that out, it ends up being 237.5. Okay, so it's one of these things where it feels like there's a decent amount of work going on, but I can guarantee that the 4 steps that we did here is much faster than writing out 25 fractions using this expression and then trying to add up all of those fractions. Okay, so that's our review of summation and sigma notation. Now, let's use this with our Riemann sum to do something a little bit more applicable to what we had been doing. And so I'm not going to draw the graph for you this time, but let's say that we're finding the right Riemann sum. Of f of x is equal to 5x plus 3 over the interval from 0 to 6 with 50 subintervals. And so kind of a dramatic increase going from 3 subintervals in our original example to working with 50. Okay, but it's still the same basic idea. We're just not going to necessarily write out everything the same way that we did before. We're still going to start by figuring out what the base of each rectangle is. So again, the textbook would call this the change of x. And the base is still nothing more than the length of our interval. In this case, because of 0, I'm not even going to write it out. That's 6 units long, divided by how many rectangles we're creating. And this is up to you in terms of whether you want to leave it as a fraction, reduce it, or write it as a decimal. I'm going to go ahead and write it as a decimal, but 6 divided by 50 gives you 0.12. Right? So each one of our bases is 0.12 units long. And then, excuse me, keep in mind that we're looking at right endpoints. So before I listed out all the endpoints, just because we were doing 3 different Riemann sums, I wanted us to be able to visualize what was going on. If we're looking at the right Riemann sum, then all I really care about are the right endpoints so that I can evaluate the function repeatedly. Okay, but the right endpoints, 0 is a left endpoint. So the first right endpoint would be 0.12 units after the 0. So it would be at 0.12. The next right endpoint would be another 0.12 units after that. It's going to give you 0.24. The next one's another 0.12 units after that. It's 0.36. And of course, we're not going to write that out 50 times. That would be ridiculous. Okay. So our objective here, kind of skipping down a tiny bit, our objective is not to write out, a bunch of addition 50 times here, but when we do our right Riemann sum, we want to make sure that we can do this using sigma notation. So we know that we are going to be working with the first rectangle all the way up to our 50th rectangle. And I guess this doesn't have to be a k equals 1. I just use a k because that's pretty typical in a textbook. But whatever you want to represent as your counter going from 1 to 50, you can say k equals 1, a equals 1, z equals 1. That's just kind of a placeholder. But the idea is that we want to add the areas of all of the rectangles. And so we know the base of every single one of those rectangles is 0.12. That's going to be a constant. We also know that we're going to multiply that times the function evaluated at the right endpoint. What's the right endpoint that's changing, right? This 0.12 is the same with every single rectangle. The right endpoint of the first rectangle versus the second versus the third, those guys are changing. Okay, so we need this right endpoint to be written in terms of a k so that we can use the same sort of ideas and formulas we had a second ago. Okay, so keep in mind here, this would be the right endpoint for k equals 1, for k equals 2, for k equals 3. So all we're doing here is looking for a pattern. What relationship can I use that goes from a k equals 1 to 0.12, or k equals 2 to 0.24, k equals 3 to a 0.36? Okay. And here, maybe it's already clear, but in case it wasn't, we got that 2.24 in that 0.36 by repeated addition. Right? We said the first right endpoint was at 0.12 because I started at 0, that's a left endpoint, add the 0.12 to get to a right endpoint. From that endpoint, I had to, maybe I should have just written this up above, I had to add 0.12, another length of the unit, to get to the next endpoint. Then I had to add another 0.12 because that's the length of the interval to get to the next endpoint. So all we're really doing is repeated multiplication. Repeated multiplication is just multiplication, and it doesn't take long to see that 0.12 came from taking 0.12 times 1. The 0.24 came from taking 0.12 times 2. Right? There are 2 0.12s creating the 0.24. There are 3 0.12s creating the 0.36. So we're taking 1 times 0.12, 2 times 0.12, 3 times 0.12. So this is nothing more than taking the value of k and multiplying it times the 0.12 in this case. So this is going to be 0.12 times k here. Okay, so that's the hardest part to get used to and maybe explain. I don't know if that was counted as an explanation, but this is just patterning. What are you doing to k to get to 0.12? What are you doing to k? So I said that right. What are you doing to k to get to 0.12? Well, you multiplied it times 0.12. What are you doing to get from k equals 2 to 0.24? Well, you have to multiply that value of k times 0.12, so on and so forth. Okay, so that's the hardest part. Everything else you can certainly just kind of look up formulas and help yourself remind of how all that works. But figuring this expression out, this is where all of the work is, regardless of whether we're talking about a Riemann sum in 5.1 or the limit of a Riemann sum in section 5.2. Okay, so we're still going to calculate that, but that's our setup. Okay, so now that we have this, I maybe shouldn't have erased everything here, so we have to remember what the function was. So the function was 5x plus 3. Okay. And excuse me. And so here, if we're doing this sum, the first thing we would do is actually evaluate this function at the 0.12k. So let's not mess with anything else for now. We just have k equals 1 to 50 of 0.12. And if you evaluate the function at 0.12k, you're just taking 0.12k and plugging into x. Okay, so all we did here was replace alpha of 0.12 and plugged in the 0.12 into f to have an actual expression there. Okay. And so at this point, there's a handful of different ways that you can handle it. I personally would go ahead and do a bit of the easy algebra / arithmetic here. 5 times 0.12 is just 0.6. And then this is completely up to you, but I would go ahead and distribute the 0.12 to both pieces. There are other ways that you can break down the sum, but if you take 0.12 times 0.6, you're going to get 0.72. And there's a k with that one, and 0.12 times 3 is 0.36. Okay. Excuse me. And now from here, you're just breaking it up. Okay, so we're kind of doing 2 steps at once. We're going to break it into a sum. And once we break it into the sum, that 0.72 can come out. Okay, so all I'm saying here is we're going from k equals 1 to 50 plus from k equals 1 to 50. Excuse me. Over here, we're just going to get the 0.36. And on the other side, we would normally get a 0.72k here, but since the 0.72 is a constant, we could put it on the outside and just leave the k by itself. And so this is where I'm just putting the sum rule and the constant multiplication rule together in one step. And so from net here, 0.72 comes down, and this is one of our formulas. We're starting at 1, going to 50 for just a k. So this is where you're multiplying by 50 times 50 plus 1 over 2. Okay, so again, this is using the n times n plus 1 over 2 formula. So that's what we get here. And then on the other part, this is just a constant that's being added to itself 50 times. And so we get 50 times 0.36. Okay. And once again, you can mess around with doing this by hand if you want, but throw that in a calculator and you're going to get exactly 109.8. Okay. And that's that. Okay. So it's, again, scary to set up. It's some notation that you're not necessarily used to using, but that's an actual kind of official Riemann sum versus what we were doing earlier in the semester when we were actually drawing visual rectangles. Right, so finally, we're ready to move into section 5.2. Everything that we've talked about so far was 5.1. What you're going to see is the only difference really between 5.1 and 5.2 is the fact that we are not going to be working with a fixed number of rectangles. We're going to be working with n rectangles and then taking limits. Okay, so let's say that we're working with the right Riemann sum. And I should maybe pause for a split second while that other example is fresh in your mind. When we're working with these types of problems, we're almost always going to be working with right Riemann sums because they're a little bit easier to find that pattern. That pattern where we got the 0.12k in that last example, if it was a left Riemann sum, it would have been a little bit more complicated. If we were trying to use a midpoint Riemann sum, it would have been a lot more complicated. So in general, because what I've said before, it doesn't really matter what type of Riemann sum you're working with, just use the easiest one, and the right Riemann sums for these types of problems is almost always the easiest. That's why we keep using the right Riemann sum here. But let's say we're looking at the right Riemann sum of f of x. Make it a little bit more complicated this time. We've got an x squared minus 4x. Let's go over the interval from 0 to 10 with, as I said a second ago, not an actual number of subintervals, but just a variable number of subintervals. So what we're trying to build up to again is if we get an expression for the Riemann sum based on n subintervals, all we would have to do is take n and take the limit as it goes to infinity, and that's going to give us an infinite number of rectangles that are estimating this function, or the area of the function, and that's going to be the same thing as the net area because of the fact that it's going to infinity. Right? So here it's the exact same process. We just have an n instead of a 50, and it's certainly a different function. So you still break it down. You figure out what the change of x is, or the base of the rectangles, however you want to look at it. And this time we're not going to get a number. We're going to get an expression. And we have to take the length of the interval and divide it by the number of rectangles. Well, the length of the interval is 10, and the number of rectangles we don't know, but we are representing with the variable n. So each base is 10 over n. And then from here, we're following the same pattern that we had before. I'm going to try to write this out a little bit more clearly this time, since we're not working with numbers. But if we're doing a right Riemann sum, we need to figure out the right endpoints. Again, since we're starting with 0, that would be the left endpoint. You're going to add the length of the interval or subinterval to get to the right endpoint. Okay, so all we're saying here is if I look at that first subinterval that starts at 0, we know the length here is 10 over n. And so if we add 10 over n, that's going to have to give us the right interval. That's all that's happening. Okay, so the first right endpoint is 10 over n. If we're looking to find the second right endpoint, then we have another 10 over n here to get from 0 and go 2 intervals to get to the second right endpoint. You have to add these together, or you get 2 times 10 over n. And again, you just keep on going. If there are a total of k, I shouldn't say k units, k subintervals, so we just say subs. So if I'm going k subintervals and I'm trying to get to that right endpoint, there's k of these 10 over n's. I'm going to have to get k times 10 over n for that right endpoint. Okay, so that's a little bit more descriptive than what I talked about last time. So if you wanted to write it out, you would have 10 over n. If you take that times 2, you get 20 over n. Take that times 2, you get 30 over n. And again, each one of these is really just k times 10 over n. Okay. So again, this idea of figuring out the relationship here from either just a pattern of what you're writing out or try to maybe visualize it this time, that is the tricky part. Okay. Once you figure out that the right endpoint is given to you by whichever subinterval you are on times 10 over n, the rest of this fits exactly the same. So we're adding up all the areas. We're starting with the first rectangle. We don't know how many rectangles we're adding up. So again, that's the same n that we started with here. But each rectangle has a base of 10 over n and a height of f of k times 10 over n. Okay. So again, to me, the setup is the harder part. So just to make sure you look over that and see where that comes from. And the rest of this is going to be a little bit obnoxious, and there's some areas you have to be careful with not to make mistakes with your algebra. But everything else is just, start to evaluate your function like we did before at that expression and, excuse me, and start putting it all together. So I guess before I erase it, let's just look at this part. If you just look at that function, all you're doing is plugging k times 10 over n into that expression. So you would have k times 10 over n squared minus 4 times k times 10 over n. Okay. And as a heads up, there's a reason I'm trying to keep the k's and the n's and all that separate. But what you get using exponent rules here is you square the k, you square the 10, and you square the n. And then over here, maybe put it as a 4 over 1 if you need to. But like I said earlier, I want to keep the k separate, so let me just start with the k. And then 4 over 1 times 10 over n. 4 times 10 is 40. 1 times n is n. Okay. So we're going to have to erase up here and rewrite this and then actually calculate it. But what we're really trying to calculate then is the sum of 10 over n times this function f was k squared times 100 over n squared minus k times 40 over n. Okay, so the rest of this is, again, using our sigma rules to actually do the calculations. And there's a handful of things that we can do pretty quickly. But first, this is the first time we were trying to work through a summation where there were two different variables within here. Okay, so remember we were talking about the constant rule and such. When we were talking about constants, we were looking with numbers before. But remember, k is the thing that's changing. K changes here, n is not changing. Okay, so even though there's a variable here, 10 over n is a constant. 100 over n squared is a constant. 40 over n is a constant because it's not changing. Once we pick the value of n, it's not changing. It's the k that's changing. Okay, so the first thing we would do is say, well, if this is a constant, we don't need to have to distribute that or do anything crazy there. We'll just put it on the outside. So this is going to be 10 over n times, I got ahead of myself, we don't need the parenthesis there, 10 over n times the sum from k equals 1 to n of k squared times 100 over n squared minus k times 40 over n. Okay. And now we can use our sum rule to break this into two different summations. And at the same time, we're going to use the constant rule to say, well, that constant can be written outside of the sum. This constant can be written outside of the sum. So we've got 10 over n. I should have equal signs here. We're going to have a big old bracket. But in this first term, the 100 over n squared is just a constant. And we're multiplying that times the sum from k equals 1 to n of k squared. And so all we're doing here is looking at this part only, not this, just this first term. The 100n squared is a constant. We're still taking the sum of k squared. Then we're subtracting, and we're splitting up our summations. We're going to have another summation here. The 40 over n is a constant. Then we're multiplying times the sum from k equals 1 to n of k. And I used the wrong symbol there. And then here, excuse me, again, you have some choices in terms of whether you want to distribute yet or not. But what we're really concerned about is making sure that we see that both of these are things that there are formulas for. Okay, so I know that I kind of just pulled this out of my back pocket because I didn't want to write it out as a formula earlier. We had already spent enough time and had enough stuff on the board. But I had mentioned that there is a formula for adding a bunch of squares up. And I always have to look this one up because it's the most complicated. But the formula for that, just look this up in the textbook on page 345. You get n times n plus 1 times 2n plus 1 over 6. And with this is the one that we have dealt with a couple of times. But the sum of just a bunch of k's is n times n plus 1 over 2. Okay. And now, I guess I would go through and simplify inside of the bracket before I distributed that 10 over n. But notice that the n here and the n squared will cancel out. That's multiplication. We're allowed to do it. So there won't be an n squared here anymore. It'll just be an n. The 100 and the 6 is going to cancel down to a 50 and a 3. And on the other portion, we get the ends to cancel again here. And the 40 and the 2 cancel down to a 20. If you want to put a 1 there, you can. And so now, this is kind of a big, long piece, but this whole thing here is one term. If I distribute the 10 times n, or it's 10 over n, I'll get 10 times 50 is 500. And then we still have, the n plus 1 and the 2n plus 1. In the denominator, we're going to have an n times 3, so that's a 3n squared. In the other term, if I distribute, 10 times 20 is 200, and we still have that n plus 1. And in the denominator, we have just the 1 times n is an n. Okay, so there's no reason to put those two fractions back together. This is exactly as far as I would want you to take it. And so that I know is kind of extreme. There's a lot of details along the way. So take your time. Problems like this can take 10, 15 minutes to work all the way through. That's why you'll see in the My Math Lab homework, I think there's exactly one problem that's like this, because I want to see you be able to do it once, but it's not something you're going to have to do with every single problem from this point forward. Okay, so again, going back to the beginning of the problem, this represents the area of all of the rectangles based on n rectangles. Okay, so finally, I'm not going to write out the details in the background here, because we've talked about the notation already, and I think I can talk through it without having to write too much here. But now let's just be aware that I guess I should maybe label this because what I'm about to write. So this is your right Riemann sum of f of x was equal to x squared minus 4x over the interval from 0 to 6. And that's what we just had. Okay, so let's say we're actually looking for the net area. So this is our definite integral notation. So if I'm looking for the net area using this notation, I guess maybe I could be a little bit more specific, but I didn't want to run out of space. But remember that the integral notation here, if there's, and we've seen this twice now, if we have the integral notation and there were no numbers, that would be an antiderivative. But this integral notation with two numbers, we are talking about the actual net area. So we're looking at the net area over 0 to 6. And notice I don't have to talk about n subintervals, or I guess I should have mentioned this over here. This is right Riemann sum over that 0 to 6 with n rectangles. But if you're looking for the net area, we're not looking at rectangles at all. There's no need to describe how many rectangles we have. But the net area, this is our definition from, or maybe not definition, but notation from the beginning of the semester. The net area between f of x and the x-axis is given by this notation where we're working from 0 to 6 of f of x dx. Okay. So I don't want to write out the crazy definition that the textbook has because it looks scary as heck. So please, if you're reading the textbook, just realize the star notation they use, all that. It looks confusing, but it's nothing more than just say, hey, find the right Riemann sum using the function and rectangles, and then take the limit as n goes to infinity. And so this is kind of a definition, but I'm not using the notation the textbook did. Okay, so this is the limit as n goes to infinity of the expression that we just found. Right, we're using the same function here, even though I wasn't clear. We're talking about the same interval to start with. So this is the limit as n goes to infinity of all of this huge expression. So a lot of this is just copying down. But you'll see here that this limit, as long as we remember rules for infinity, this limit is a piece of cake. And so that's the nice thing. If you can come up with the Riemann sum, finding the limit is almost never a big deal, but finding the Riemann sum can be a big deal. And so again, all we're saying now is that the actual net area would be what we get if we have an infinite number of rectangles, so that we're kind of almost looking at just a bunch of little line segments that we can squeeze between the graph and the x-intercept, sorry, the x-axis. Right, so this goes back to our limit rules. Remember that this only works when we're working with infinity, but if we're working at infinity and we're looking at individual polynomials here, at infinity, only the term with the largest exponent matters. Okay, so when we look at this first polynomial, and the 500 is a single term, it has to stay. In this polynomial, the only thing that matters is the n. In the second polynomial, the only thing that matters is the, again, term with the largest exponent, which is the 2n, and the 3n squared down below is a single term. Okay, so remember, you have to be careful. This is polynomial by polynomial, not expression by expression. So here, that has to stay. Ignore the 1, ignore the 1, that has to stay. In the second fraction, same basic idea. The 200 is a single term. It has to stay. We can ignore the plus 1. And of course, the n has to stay. And then finally, you can see that all those n's cancel out. Right there, you know, if you put this together, you get 2n squared, and the n squared and the n squared are going to cancel out. Over here, the n's and the n's cancel out. So there's no more limit that we have to worry about. We've dealt with the limit. What we're left with is 500 times 2, which is 1,000 divided by 3. And then we're subtracting 200. Okay. And again, this depends on you know, how you need to do it. You know what my math lab might be asking you to do if you ran into this problem. But 1,000 thirds minus 200 is the same thing as 400 thirds. Like, wait, yeah, 400 thirds. But as a decimal, that's 133 with the 0.3 repeating. Okay, so this is the first time in this class that we found the exact net area of a function that was not either a line or a circle or an ellipse, something that we had a formula for. Okay, we had a random, I don't even remember what it was offhand now, I think it was x squared minus 4x. That's a parabola. It doesn't fit any of our nice geometry shapes, but this is how we find the net area. Okay, so we're going to do one more example, and then we'll finally finish with this particular lecture. I brought my eraser again. So now that we've kind of been introduced to the idea, let's do this one more time. And hopefully, the second time around, it'll feel a little bit more comfortable. I know that I kind of led us into it instead of just giving us a problem. But let's say this time around that we're starting with that notation where we're finding the net area over the interval from 0 to 5 of the function 4 minus 2x. And we're going to do this two different ways, just to tie it back into geometry, and we're also going to use the Riemann sums so that we can check answers, make sure that you know, what I said earlier is actually correct and makes sense. Okay, so if we do geometry here, we actually have to have a visualization, so we need to sketch the graph. So this is not going to be perfect. But we're just sketching the graph between 0 and 5. So you could use slope-intercept form if you want, but the easier way is just to plug in 0 to get 1 point, plug in 5 to get another point, and connect the dots. So if I plug in 0, you're going to get 4. So that's the first line. If I put in, sorry, first point, if I put in x equals 5, 4 minus 10 is negative 6. And of course, I have to go over to 5 as well. So there's 5, negative 6 over here. And I missed terribly. So I guess I should point this out. So that since we are going across the x-axis, we need to know where that point is, right? Because if I'm looking at the area between the line, I guess in this case, in the x-axis, I'm going to get a triangle here and I'm going to get a triangle here. So I need to know what that point is. And I know that I missed because of what I should happen. But if I'm looking at the x-intercept, the x-intercept happens when the y value is equal to 0. And I think everybody in here can solve this without actually showing any work. You should be getting x equals 2. So I apologize that I missed so badly here, but let me just kind of cheat and move the line over a little bit so that we can see that that's 2. Okay, so at this point with geometry, this is a piece of cake. We know the height here is positive 4 since above the x-axis. The base of the triangle here is 2. With the other triangle, this base, I know it's squished together, but that should be 1, 2, 3 units here. This time we're below the x-axis, and so the height is -6. So putting it together, we're looking for net area, but I'll just use A for area. The area of this triangle is 1/2 base times height. And the area of the other triangle is also 1/2 base times height. It's just this time our height is negative. Okay. And the rest of this is just nice quick arithmetic. So here the 1/2 and the 2 cancel out, you left with a 4. Here the 1/2 and the -6 we cancel down to a -3. So you get a 4 plus a -9. 4 plus -9 is equal to -5. And so that's again a quick review of stuff that we had done previously. It makes sense that this is negative because that triangle is definitely larger than this triangle. So with that being below the x-axis, it makes the whole net area negative. Okay, so I'm just going to go ahead and write it up here. We've actually found the net area using geometry exactly here. Now that we've done that and reviewed and all that, let's go through and use a Riemann sum to do this one more time and show that as we take the limit as n goes to infinity of a right Riemann sum, that it's also going to give us the number 5 up here. So, just as a heads up, if you were doing a random problem, this wasn't part of a lecture, and somebody said, hey, find the definite integral of this expression, geometry is absolutely the fastest way. So, don't do anything crazy if it's not asking you to. But if the textbook asks you to find, excuse me, you might say something like this: use a right Riemann sum. Riemann sum and limits to find the net area. So it would typically, try to restate this. It's just already on the board. So it'd say use right Riemann sum and limits to find the net area. It might also say find the use the limit definition of net area to find the net area. But this is what we're doing: is use the right Riemann sum and limits to find the net area. So if we're using a right Riemann sum, we have to once again know what the base of the rectangle is, and just watch our notation. Our notation says it's going from 0 to 5. So the length of our interval is going to be 5. And we're using n rectangles again. So that just has to be n. Okay. So again, anytime you're looking to find the actual net area or finding a limit that goes along with Riemann sum, you have to have an n for the number of rectangles, or some variable at least for the number of rectangles that you're dealing with. Okay. And then from here, we're looking at right endpoints. And now that this will be the third example, I guess, where we've seen something like this, so hopefully you can kind of start to see a pattern. As long as we're dealing with the right Riemann sum, and as long as we're dealing with a 0 here, then the right endpoints follow a nice little pattern for us. So I can draw it out again. Maybe that's not necessary, but if there's 0, we have to move over 5 over n units to get to the first right endpoint. We have to move 2 5 over n units to get the second endpoint. And so every one of these, sorry, not the 2 there, every one of these endpoints can be found by just multiplying how many intervals we have. So if there are k intervals, we have to take k times 5 over n to find the kth right endpoint. Okay, so the right endpoint that we're looking at here is just k times 5 over n. And again, just kind of rewind the video or go back in your notes. When we had the 10 over n, we ended up with k times 10 over n. When we were working with the 50 subintervals, so I believe it was 0.12. In that first example, we ended up with k times 0.12. So that is a pattern that you can use if it helps. And then finally, we put this together. We know that we're looking for, let me do this. If I'm looking for the actual net area, we have to realize we're going to take the limit as the number of rectangles goes to infinity. But the actual Riemann sum runs from k equals 1 to n of the base of the rectangle times the function evaluated at the right endpoint. Okay, so that's just kind of the shorthand notation for what it looks like. I don't want to carry this limit through the rest of the problem. We'll do the limit as the last step, so let's get rid of that. So this is what we need to find an expression for that doesn't have the sigma notation, and then we'll just find the limit. And likewise, I kind of got it a little bit ahead of myself. I just used some notation here. The first step would be to actually plug k times 5 over n into the function. And so we're looking at 4 minus 2 times that k times 5 over n. Okay, so once again, the rest of this is just be careful with the different rules that we've talked about and don't go too fast. But if we evaluate this to get an expression and then take the limit as n goes to infinity, I should be getting a -5 up there. Okay, so as we've done before, this is a constant with respect to k. So the first thing I would do is take out that 5 over n. We're multiplying that times the sum from 1 to n of the rest of this. So 4 minus, and we might as well multiply all this together. This is not the distributive property, that's all multiplication. So it's just 2 times 5 is going to give you a 10 up there over n. And again, keep that separated from the k. Right? And maybe put parentheses here just to make sure it's clear that that's all part of the sum. And then from there, break this down into two sums. So we have the sum from k equals 1 to n of 4 minus the sum from k equals 1 to n. This time around, again, that 10 over n is a constant, so we'll put it on the outside and just deal with the k. And then finally, plug in the results from the formulas that we've had. So here, if I add 4 to itself n times, you're going to end up with a 4n. And this other one, we have a 10n on the outside, but we've seen this a handful of times now. For adding up a bunch of k's up to n, the formula for that is n times n plus 1 over 2. Okay. And then finally, simplify what you can, distribute all that sort of stuff. So notice here that n's cancel out, the 10 and the 2 cancel down to 5. And then if I distribute that 5 over n, here, 5 times 4 is going to give you 20. The n and the n are going to cancel out, right? Dividing by n, multiplying by n cancel out, so that's just a 20. And in the other side, we end up with 5 times 5 is 25. We still have that n plus 1 in the numerator. And then now we also have an n in the denominator. Okay, so that's our expression for the Riemann sum with right endpoints with n subintervals. And so now it's just a matter of taking the limit. So I apologize, these problems are long enough that I have to keep erasing and starting over at the top. But now that we have that expression, we know that we can find the net area by taking the limit as n goes to infinity to have an infinite number of rectangles. So we're finally at the point where this is equal to the limit as n goes to infinity of 20 minus 25 n plus 1 over n. And this goes even faster than the previous example. It's still the same idea, where as long as we know that we're going to infinity, the only thing we care about within a polynomial is the term with the largest exponent. So here, just again, don't go too fast. We can't just say, well, the only thing that matters then are the two n's. That 20 is a standalone polynomial slash term. 25, standalone polynomial slash term. That's a whole polynomial. We don't care about the one, so we're just going to be left with an n there. And the n is its own standalone term. And so you can see immediately the ends cancel out. And so the limit is just 20 minus 25. And 20 minus 25, surprise, gives you a -5. And so that just verifies that what we were doing geometrically and what we were doing using the Riemann sums completely matches up. Right, so that's the end of the lecture. I know that this, sigma notation especially can be very tricky. It's not something that a lot of students have had a lot of experience with before. Just do your best to get through an example using the video. But after you do an example or two, if it's still really unclear, just let me know and I'll do the best I can to work with you.